Welcome to this explainer. If you look around right now, literally almost everything you interact with is a mixture of some kind. Today, we're embarking on a really fascinating journey to figure out exactly how we can unmix the world around us. Because taking these complex mixtures apart, that's a superpower, and it's exactly what we're going to master today.
But have you ever stopped to wonder how we actually get those pure, sparkling white sugar crystals out of tall, green sugarcane plants? Or, for that matter, how doctors can detect diseases like malaria using just a tiny drop of blood? Well, it all comes down to the science of separation. This isn't just dusty laboratory theory. It's the hidden mechanism behind the everyday things we consume and the life-saving medical techniques we completely rely on.
So here's our roadmap for today's explainer. 1. Understanding different mixture types. 2. Calculating solution concentrations. 3. Decoding solubility and temperature. 4. Advanced separation techniques. 5. Centrifugation and coagulation methods. And 6. Practical applications of separation.
Let's dive right into Section 1, Understanding Different Mixture Types, Sorting the Uniform from the Messy. Okay, so right off the bat, there's a clear divide in how things mix together. On one side, we've got homogeneous mixtures, which we also call solutions. These are perfectly uniform throughout. Every single sip of a well-mixed sugar solution or a soda is exactly the same. But on the other side, we have heterogeneous mixtures. Think of stirred sand and water or muddy water. They are absolutely not uniform, and if you just leave them alone for a while, the heavier particles simply settle right to the bottom. Now here's a really cool trick. If you shine a laser pointer through a true homogeneous solution, like clear salt water, the light passes straight through invisibly. There's nothing to bounce off of. But if you shine it through a heterogeneous mixture, specifically something called a colloid, like water mixed with just a few drops of milk, the suspended particles scatter those light rays, making the actual beam visible. This is known as the Tyndall effect, and it's a super quick visual way to identify exactly what kind of mixture you're dealing with. Before we move on, I want to highlight something that actually surprises a lot of people. Even solid metals can be homogeneous mixtures. We call these alloys. They're created by melting metals down at really high temperatures, mixing them up, and letting them cool back into a single solid. And unlike sand and water, you can't just use simple physical methods to separate the components of an alloy once it's solidified. They are locked in.
Moving right along to Section 2. Calculating solution concentrations, the vital math of mixtures.
So getting the exact proportion of solute to solvent right isn't just an academic exercise. It's a matter of profound importance. We use mass by mass by volume, and volume by volume percentages. Why does this actually matter in the real world? Well, consider a hospital saline drip. It is strictly a 0.9% mass by volume solution. That precise concentration safely replaces lost fluids in the human body. If that math is off even slightly, it goes from being a life-saving treatment to a very dangerous medical mistake. Let's actually walk through a simple calculation straight from the text so you can see how this works. Say you have 10 grams of salt, that's your solute. You dissolve it in 90 grams of water, that's your solvent. You add those two together to get a total solution mass of 100 grams. Then you just divide the solute by the total solution, multiply by 100, and boom, you have a 10% mass by mass concentration. This specific kind of math is absolutely necessary for everything from whipping up an oral rehydration solution, or ORS, at home, to making sure a farmer mixes agricultural pesticides safely and effectively. Which brings us to Section 3, Decoding solubility and temperature, pushing the limits. This begs the question, exactly how much of a solid substance can a liquid solvent hold before it simply refuses to absorb any more? Well, when we map out solubility across different temperatures, something really striking happens, especially with potassium nitrate. At 10 degrees Celsius, 100 grams of water can only hold 21 grams of it. But if you heat that water up to 80 degrees, suddenly it can absorb a massive 167 grams. So heating a solvent essentially forces it to absorb way more of a solid substance than it normally could. All right, let's get into the mechanics of it in Section 4, Advanced Separation Techniques, the Art of Unmixing. These two methods represent the absolute magic of physical states. Remember a minute ago how we talked about hot water holding more solute? Well, crystallization takes advantage of that. It takes a hot, heavily saturated solution and slowly cools it down. As it cools, the liquid can no longer hold all that solid, forcing it to crash out and form beautiful, pure crystals. This is literally how we get our table sugar. Sublimation, on the other hand, is wild. It's when a solid turns directly into a gas. So, if you have a mixture of sand and camphor, applying heat will cause the camphor to just vaporize completely without making a single drop of liquid, leaving the pure sand perfectly isolated behind.
Now, what about separating liquids that are totally mixed together? We call those miscible liquids. For this, we use distillation, which relies completely on specific boiling points. By carefully heating the mixture, the liquid with the lower boiling point turns into vapor first. It travels up, passes through a condenser to cool down, and drips perfectly into a new flask. As long as those two liquids have at least a 25-degree temperature difference in their boiling points, you can pull them apart flawlessly. And if the boiling points are closer than 25 degrees, we just step it up to a slightly more complex setup called fractional distillation to achieve that exact same separation.
You know, sometimes chemistry shows a really poetic side. Have you ever wondered how forensic scientists or chemists separate different pigments in ink or natural dyes? They use paper chromatography. And get this, it literally translates from Greek as writing with color. By placing a tiny dot of ink on specialized paper and dipping just the very bottom edge into a solvent, the liquid starts traveling up the strip. The different color components move at different speeds, eventually spreading out into this beautiful separated rainbow right across the paper.
But what about those super stubborn mixtures, like oil and water, that just flat out refuse to mix uniformly? We call those emulsions, or immiscible liquids. Since they don't mix, we can rely purely on differences in their density. We pour the mixture into a really handy glass tool called a separating funnel. Because the oil is less dense, it just floats right on top of the water. Then we simply open a small valve at the bottom, called a stopcock, carefully drain away the heavier water layer, and shut the valve right before the oil comes through. It's so simple, but so effective.
Next up is Section 5, Centrifugation and Coagulation Methods, Forcing Separation.
Normally, centrifugation uses rapid spinning to force heavier particles outward. It's exactly how modern hospitals separate red blood cells from plasma. But electric centrifuges are expensive and, well, they require electricity. Enter this brilliant invention, the paperfuge. Inspired by an ancient spinning button toy, it's a hand-powered centrifuge made out of little more than cardboard and string. It actually spins blood samples at incredibly high speeds to detect malaria in remote areas, costing mere pennies and requiring absolutely zero electricity. Talk about a game changer.
Now, when spinning just isn't an option, say you've got a beaker of cloudy, muddy water that just won't clear up on its own, we use the incredible power of coagulation. By adding a coagulant, like powdered alum, it actually acts like a microscopic magnet for all those tiny, stubbornly suspended mud particles.
And you can see the result here. The alum causes that fine mud to suddenly clump together. These larger clumps are finally heavy enough to submit to gravity. They settle right down to the bottom in a process called sedimentation, leaving this beautifully clear water at the top that can simply be poured off or decanted. It is a wonderfully simple, incredibly effective way to purify water.
Finally, we reach Section 6, Practical Applications of Separation, from History to Sustainability. What's wild is that we can actually trace these exact scientific principles back centuries. For instance, ancient Indian coastal communities were basically master chemists long before modern terminology existed. They actively applied boiling and evaporation techniques to harvest distinct types of salt. They created ponga salt by vigorously boiling concentrated sea brines and harvested Karkach salt crystals directly from the slow, natural evaporation of seawater. Similarly, the ancient city of Connaught mastered the complex art of distillation centuries ago to extract botanical oils, creating these world-renowned perfumes. They were utilizing these exact principles flawlessly. Fast forward to today, and these exact same foundational principles of separation scale all the way up to global sustainability. Think about it. Waste segregation is quite literally the unmixing of human-made mixtures. Separating plastics from metals and organic matter from recyclables is absolutely essential to keeping our world clean, healthy, and sustainable. So every time we recycle, we are simply applying the science of separation on a massive industrial scale. I'll leave you with this final, really provocative thought, straight from our source text. We've seen how effectively we can pull apart the components of human blood using tools like the centrifuge. But as we truly master the separation and analysis of these life-giving mixtures at a microscopic level, do you think we're getting closer to synthesizing a universal artificial blood substitute? One that could potentially save millions of lives without ever having to rely on human donors? The answers to questions like that lie in the very science of mixtures we've explored today. Thank you so much for joining me on this explainer. Keep asking those big questions, and I'll see you next time.